All right, any questions from last time? So I stated this poorly, that two Hager diagrams correspond to the geomorphic Hager systems. First slide if you remember.
Yes.
Cool. All right. So I really want to talk about spines and groups. So what does this mean? Well, I defined in passing the spine of a handle body, so let me just restate it. A spine of a handle body H is an embedded graph gamma inside the interior of H such that if we remove a neighborhood of gamma from H, what we get is something, we get the product of boundary H cross I. Something that's homomorphic to the boundary of H cross I. And then we say that a spine is dual to a cut system of, so the spine gamma is dual to a cut system of disks D for H. If it has G edges, maybe it's E1 up to EG, such that the intersection of EI with the disk DJ, which is the labeling of our G disks, is Kronecker delta. So they intersect when they have the same index and they're disjoint. They intersect once when they have the same index and they're disjoint otherwise. Okay, let's look at spine dual. Okay, let's look at kind of what we're talking about. So actually this definition of spine is quite a bit more general than what we'll actually use in practice. So maybe I'll give sort of a more general picture here. Maybe something like this. So let's actually have a graph that actually has a couple of vertices. Something like this. And then maybe it has edges like this. Something like that. So that might be our graph. And so then what does it mean for a cut system of disks to be dual? Well, this is where we'll lose a little bit of our generality. What we see is that for each edge, there is a disk that intersects that edge in a single point. Something like that. Did I do it right? I think so. So this is not what we've been calling a cut system of disks, but it's sort of an enlargement of a cut system of disks. And in this more general setting, it's still interesting because a nice handle structure on the handle body coming from the graph, where at each vertex we have a 3-ball or a zero handle or a 0 cell, and for each edge we have basically a 1 handle connecting those 2 3-balls together. Okay, but in the case we're most interested in, we'll have something that looks like this. We'll have let's see. We'll have just a single vertex, and then we'll have an edge that runs through each one of these disks like this. So this will be E1 D2, and D3, and they're dual to D1, D2. Okay. And I guess the condition, oh yeah, so it needs to be embedded in such a way that if we removed it, we would deformation retract. Or another way to say it is that the handle body should deformation retract onto the spine. Okay, and so notice with spine gets used twice in two different ways in the trisection community now, because we talk about the spine of the trisection or the bridge trisection. We also talk about the spine. Of course, this is the more classical version. Okay, any questions about that?
In the first picture, what are these red discs?
What are the red discs? Yeah, there's sort of there's some sort of an enlargement of a cut system. So maybe if we had our original discs, D1 and D2, well, this is just a parallel copy of D2, right? And this is just a parallel copy of D1. And this is, a third disc, which can be obtained from D1 and D2 by sliding. So in general, you can maybe think about a system of discs for the handle body as being any sort of collection of disjoint properly embedded discs. Maybe that they're all essential, so we don't allow boundary parallel discs. And in that case, you're going to cut your handle body, instead of having it, when you serger along the curves of the discs, instead of getting a 3-ball, you're going to get a disjoint collection of 3 balls. When you have a picture like this is like having a Morse function on the handle body where there's a single minimum and a bunch of critical points of index 1. Here we have multiple minima, and we have it can sometimes be useful to this. In particular, people often will throw in D1, D2, and D3 so that the surface gets cut up into pairs of panes. So there's no parallel curves or parallel discs, but there's as many discs in the handle body as you can have without having any parallel curves. That's to call it pants decomposition. Okay. Any other questions? Okay. So we have a lemma. So I guess I'll leave as an exercise. It's got just 3 sort of statements to verify. Every cut system of disks is dual to a spine, or has a dual spine. Conversely, and here's where we're losing generality for the present development. Every, say, 1 vertex spine is dual to a cut system of disks. Okay. And then the third one, which is probably the most interesting, 2 spines that are dual to the same cut system are isotopic as spatial graphs. So basically what this is saying is we have a really nice correspondence between cut systems of disks and spines of our handle bodies. And we can make this correspondence even a little bit better by considering something called edge slides. Okay, this is a definition. All right. A spine gamma prime for H is the result of an edge slide on a spine gamma of H, and then maybe we would say of an edge E sub I over an edge J. Is that how I do it? J, E sub I, and E sub J are edges in our original graph gamma. If the following setup is sort of following set of folds. So the first thing we want is let's write gamma as the union of G edges, and let's write gamma prime as the union. If gamma is the union of the edges, of these edges, in particular, let's throw in e sub I, then gamma prime is the union of almost all the same edges except with a different e sub I, as you might expect. And then the second condition is that e sub I and e sub I prime are sort of geometrically related in a nice way. In particular, there exists a triangle, delta, inside the interior of H, such that the boundary, I guess there's some conditions here. Such that delta intersect the unit, so delta intersects the spines. This is contained in the interior, I guess equals the boundary delta, maybe equals. That's right. And the boundary of delta can be written as omega I union EI union omega I prime, such that omega I is contained but not equal to this is supposed to be EJ. Sorry. I got it right. Okay, that's supposed to be EJ. Omega I is contained but not equal to EI. Omega I prime is contained but not equal to EI prime. And furthermore, we can ask that delta be contained in a regular neighborhood as EJ. And then I guess the last condition is that given all of this, e sub I prime is what you get if you take e sub I, remove the arc omega I, and add on the arc. So we have some parts. In this case, we have EI, or this is EJ, this is EI. And we have this triangle, which looks something like this. Remember, this is meant to be supported in a neighborhood of EJ. So I can sort of think of it like this. And so one edge of the triangle is EJ. I guess I said out loud that the triangle is embedded, but I guess it's not. So it's good that I didn't write it down. So here is gamma prime is, of course, gamma prime looks the same as gamma everywhere else. It still has EJ in it, but now it has a new edge which looks like this.
Do you want to allow not sliding along the entire length of an edge?
No, we're meant to slide along EJ. So this triangle is meant to tell me how to take EI and take this.
So I thought you were going to have the edge of the triangle be EI, EJ, and EI prime. You could make that.
You're saying I could just draw that all the way around?
Yeah, I know that. So it's sort of like a pair.
So that would maybe be a little bit more natural. But it's not a partial slide.
Right.
It's that we're only,
Yeah.
it's sort of, it's supported here. But you're right, you could kind of have it supported there. Yeah, so that should be the same thing.
I mean, it's sort of analogous to defining a handle slide as the other.
Oh, yeah, you're right. Mm-hmm. Yeah, you're right. That's probably a little bit more natural. Okay, then the triangle will be even less embedded. Yeah. All right. So, okay, implicit in this is the fact that gamma prime is a spine for H. Gamma prime is a spine. So I'll leave this as an exercise, but you want to show that removing a regular neighborhood of this new graph still gives us a surface cross-eye structure. Okay.
Can you just trace out the triangle?
What?
Can you trace out the triangle?
Can I trace out the triangle? Oh yeah, it's this. That's one edge. E sub j is another edge. And then this is another edge. So if I broke it, you know,
Two vertices.
it's a triangle with two vertices. Yeah. Or this comes all the way. Right, and if Dave had his way, it'd be a triangle with one vertex. Or just like it's like a parachute. Okay, so why consider such a thing? That these edge slides correspond with disk slides. So, I mean, we already saw that spines sort of correspond uniquely to cut systems of disks, and we know we can change the cut system of disks by a disk slide. So we would hope if you're doing this edge, we would be changing the corresponding way, and that is the case. So if gamma and gamma prime are spines for H such that gamma prime is obtained via an edge slide, let's say of E sub, what did I do? E sub I over E sub J, just like we've been talking about on gamma. And D and D prime are cut systems of disks dual to gamma and gamma prime. Then D prime is obtained via a disk slide, or I guess maybe I call this a handle slide. Let's call it a disk slide today. The disk slide of D sub j over D sub I of this other. Okay, maybe I can reuse these pictures. Okay, so in the sort of original setup, we have this dual disk system right here. So I guess this would be DI, and over here, this would be DJ. And what we see, I'm sorry, I misled. This goes my J and I are backwards. This is DI and this is DJ. And so what we see over here is we can still have DI hanging around, but we don't want to have DJ anymore because it would, you know, it would intersect EI prime and EJ. So what we do is we can actually sort of use, well, I guess I think this is not quite well defined, but there are various ways to do this, but we can use the some portion of this triangle, I guess these segments here, to tell us how to do a slide. And the answer is that if we slide over this, something like that, then we get a new disk. So what does this look like? It goes in. This is a trough, I guess. Disk, trough, disk. And well, this new disk DJ prime is actually going to be on the rack of the surface, and it's actually sits right there. Maybe I'll just draw the end result. It's this guy here, which you can see. I mean, the slide we take there, we slide it over DI, and we get this. noticing that this is not the unique disk that has that property. I also could have slid DJ on an arc that, say, started off the same way, but then wrapped around a bunch of times, and then ended up there. In fact, I guess sliding on. Let me think about this for a second. I thought that would be okay, but now I'm not so sure. You know what? I'm going to change my mind. I'm going to say that this is actually the only way to do this.
So we slid EI over EJ, and that corresponds to sliding DJ over DI.
Correct. Okay. Yeah. Yep, it's backwards. Yeah, so the reason this is unique is because there should be a unique way below this spine. No, I'm confused. Well, let's see if I can unconfuse myself on the fly. Let's suppose we did a different slide. I want this to be my disk over here, and now I'm instead going to slide maybe something like, oh yeah, so let's do two just. Okay, so this is maybe a picture of a slightly more complicated slide of dj over di. Just close down to. This is fun doing this on the fly like this. Accelerating. Okay. So it's tidbit. I think we got one's all the way over here. Okay. That's stuck there. That's there. And
If you want to get around the S, like twist around a lot to get back.
yeah, that's point down. Okay, so if it does, it's sort of going under this and then over here, the topic in the handle body.
In the handle body, that is isotopic to this. Because, yeah, if you ignore the disk,
I don't know, I think it's caught on the holes. I mean, there's a.
But those twists in the handle body, you just pull it into the middle, that whole middle section where it's twisting around.
Oh, yes, that's right. That's the point. Yeah, so, okay. So any slide will work. And the point is that, I mean, the slide you really want to do is somehow dictated by this sub arc of this bit of the graph here. And what you kind of want to think about doing is you want to think about flowing that onto the boundary of the handle. There's going to be lots of ways to flow that onto the boundary. In particular, I've sort of drawn one thing that can happen, which is that as you go out, you can sort of twist up this way. And I think you could even twist other ways. But the point is that all of these things are isotopic. So the point is that there's lots of arcs on the boundary of the handle body that become isotopic into the spine. Yeah, so okay, yeah, this is that, like, if you have this curve on the boundary of this, on the surface, well, inside this handle body, this curve is just isotopic to a core. Because, and the indeterminacy here is twisting along the cut disk. And the indeterminacy here was twisting along this cut disk, right here, which is separate. Okay, so one thing that the spine perspective is useful for is understanding the fundamental group of the handle body, and then of the given handle body H, and a spine gamma dual cut system D or H. And we can let that be the union of these G edges. We have a presentation for the fundamental group of H, I guess relative to V, where V is the boundary of the edge of all the edges. And what is this presentation? Well, this should be a free group, and the generators are going to be letters x, i to x, g. There'll be no relations, and each xi should be the class of the edge ei inside the fundamental edge. Okay. So we just take as our generators the loops e sub I. Okay. And okay. So now let's see. Oh, so I guess two comments. Maybe I'll just make two comments for now. So so now we are choosing an orientation. Choosing orientations for the edges e sub I, right? And so edge slides are going to correspond to a certain type of tsetse move. I was going to maybe talk about this more in the future, but I guess I'll just save this for now, right? If we slide, so let's see if I can figure out how this works. So if we slide E I over E J, then this is like taking it's like taking our generator set x1 to xg and changing it to with xi in it, changing it to a new generating set where we want to do this in an oriented way. Okay. So let's orient this like EI followed by EJ. So, or XI followed by XJ. And there are other of these tsetse moves that are relevant here. One is sort of changing the generator, and that would just correspond to changing a choice of orientation for one of these guys. And then I guess maybe there's another one that's sort of permuting the generators, which would correspond. And so yeah. At some point I'd like to say something about like, but I don't think I want to do that now because I wanted to jump up to actually calculating the group of 3 manifolds. So let's do that now. Any questions? Okay. Let's suppose the middle attached along a curve theta in. So the example I want to keep in mind here is okay, so this is, I think, what I want to think about as theta. And so let's draw our alpha disks. So here we'll have, this will be alpha 2, and this will be alpha 1. And they bound disks, which are, and these are going to get inherent orientation, so let's orient them up. And they bound disks that are dual to this spine I've been drawing, which is this guy. This guy here. So I guess E1 should be oriented that way, and similarly E2 should also be oriented that way. So this is the step here. So what we want to do is we want to calculate the fundamental group, how the fundamental group changes by attaching this two-handle along theta. The fact is that the class of beta inside pi 1 of the handle body can be determined by counting, by recording the intersections with the alpha, which is the boundary of D, which is where D is dual to gamma, which is the union of edges, and the class of EI xi. So what we see is that phi 1 of H union H is going to be disk along that, so that homotopic class. Okay, so what does this have to do with counting the order? Since we sort of want to think of this as being relative to the space point, well, one thing you can do is you can, like I was saying before, you can push this graph. Maybe I'll just think of it like this as lying in the boundary. And then we can homotope the curve beta so that it looks like a wedge of loops that's based here. So what that's going to look like for us is something like this. So these guys are going to have to come in here and come here, go around. I think we want to come into here, into here. Well, anyway, everything has to come in. So it looks like this. And then there's two things that go like this. They go back here maybe. And okay. So I think this bouquet of curves is what you get if you sort of drag everything so it looks like a little curves. Now, one thing you see is that these look like the E1 and the E2 elements, but then there's also these guys that wrap around in this way. But since there's a disk here, these loops are actually no longer so they're not. But But the point of that is that if there's a way to make beta, look like a based homotopy class here, and if we remember the order in which we came in and came out at this point, we would be following along beta and just recording. Okay, so then the other point is every time we do a loop, a copy of x2, okay? But every time we do a loop like that, we're actually hitting the curve alpha2 in an oriented way. So what we want to do is just record the orientation. So if we start, we hit alpha1 twice. So we write down two x1s. And then we go under here and we hit alpha2 again. And then, so the order of intersections was 1, 2, 3, 4, 5. And then we run back here and we're back to where we started. We hit x1 the fifth time. And so the word that we get, the class of beta, is x2, x1 squared, x2. The metal group would be x1, x2, mod this word. And if we then attached another two handle along the surface, so this surface, this genus 2 surface down to a genus 1 surface, if you touch one more two handle to get a sphere and cap off, then we would get another relation. Okay, and this then would be pi 1 of some 3 manifold determined by the Haggard splitting H alpha. We attach 2 bit of this. Okay, so the upshot is
So, do you have to choose beta in a region that is connected to the base point by path and disk?
I don't think so, because moving beta onto this point is kind of like a finger move. So if I move this, I would hit this with opposite.
But isn't it going to change the order?
Well, no, because you'll travel. So you'll go in and maybe you have all these extraneous intersections, but then when you come back out, because you're doing this, you're running along where you run in, and then you come immediately back out the way you came and continue along the way, right? And so anything that this sort of homotopy hit, you would immediately undo. That kind of makes sense. Say instead of, say.
The blue dot you drew on the far right,
Uh-huh.
you went there to the base point across.
Oh, like if I went around this way?
No, straight across, straight.
Just,
Yeah.
uh-huh.
Then you're gonna hit, at the beginning of your word.
Right, the first thing then I'd read off would be x2,
Right.
and then the second thing I'd read off would be x2 inverse. Because I immediately come back out.
Oh, that's your, I see. I thought you were starting at the base point.
Well, okay, because then what my loop would look like something like this, right?
It depends on where you're starting from.
I mean, the x1 and x2 coordinates, they have base point in the middle. So, I mean, either way, if you cyclically permute a relation, it's still a relation, so it doesn't matter.
Right. That's right. Yeah, probably when I pull this spine onto the surface, we have this issue of twisting and stuff. I think that's where
Yeah.
you might end up getting conjugates of your relation. If you're sort of running it, every time you have to run to the base point in a complicated way. But yeah, again, it's just gonna be, yeah, exactly. It's just gonna be a conjugate, so cyclically it will reduce to this. Yeah. Okay. So what we see is that if y equals if sigma alpha beta is a Hagar diagram for y, then what we see is that we get pi1 of y has a presentation which looks like xg and then g relations, where xi is just the, well, like I said, it's the homotopy class of the edge ei, which is dual, where ei is dual to alpha I. So in a sense, you can think about the generators as the alpha I in some sort of dual sense. And then the relations, Ri, these are just the Rj, these are just the homotopy classes of the curves Vj from your diagram. So you can totally calculate the fundamental group from the Hagar diagram by just orienting curves and recording intersections in the right order. Now, I guess if all you want to calculate is homology, then now you don't actually even need to worry about recording the order that you hit the curves in. You just sort of care. You just get a matrix that tells you with sign how many times each beta curve hits each alpha curve. So the homology calculations. Okay, so let's just record this as a proposition. How fast? Y is a 3-manifold that admits a genus G Hagar splitting, then pi1 of Y has a balanced, pi1 of Y has a balanced presentation of rank G. And this is worth writing down, so definition. The Hagar genus of Y is the quantity G of Y, which is the minimum among the genus of surfaces sigma, such that sigma is a Hagar surface for Y. And so what we see as a corollary is that the Hagar genus of Y is bounded below by the rank of the fundamental group of Y. There was a rank versus genus conjecture. Which and this was first shown to be false in, I won't write this down since we're out of time, but I'll say this and then I won't return to it. In 1987, Wallow and Zisheng showed that there are some separate fiber spaces for which you can prove the genus is 3 and the rank is 2. So then the conjecture evolved to what about, and then that was followed up by work of Schultens and Wittmann, who showed that you could, by taking graph manifolds, by sort of gluing them on tori, you could get this you wanted. But for a long time, it was open whether or not this was satisfied by hyperbolic manifolds. And that wasn't proved until, I guess, around 2013 by Towley, and he gave hyperbolic examples where or disproved hyperbolic examples where the rank and the genus differed by arbitrarily much. I was supposed to state an exercise at some point. And the exercise was to calculate some groups. And I think what I had in mind was we have these length spaces and we have these 3 torus. that we gave diagrams for. So you can go calculate the groups of those guys.
How about another exercise? Show that z to the 4 is not a 3-dimensional group.
Okay.
There's no 3-dimensional group.
Did this come up in while I was talking?
I think so, yeah.
Wasn't it a bit involved or?
Well, I mean, at least the intuition is not. Yeah, actually, I don't know how you really show that, but the idea here is
Oh,
that
that's fine, it can be hard.
you might think it does, you might first just intuitively see why it can't have a presentation of this kind.
Yeah, great, no, I think that's a wonderful exercise. For you. Okay, all right. Trying to plow through some of this Hagar theory so we can get the trisections. That's my goal. We're getting there. This will all pay dividends, I suppose.